Hello, this is the Tepid Coder. In this episode, I want to talk about unions, structure alignment, and Bitfields. So, let's do that. Stream. So, we've gone over structures previously. I have something like struct. Let's call it some structure. We can put some fields in here. Now, something I didn't quite cover was things about alignment in the structure. So if you have something like a uint 32t, let's say, let's actually include, hold on a second, C standard int, so I can use that. And I have like UI32 something. And down here I have UI, let's say, uint, how about 8t? UI8, small number. Okay, so far we have 5 bytes in here. 32 bits is 4 bytes right here. I'm gonna label these 4, here's 1 byte, it's 8 bits. Now, if I put something else in here, we have something like uint 16t, UI 16, slightly bigger number. This is going to be 2 bytes, right? I could even have something like a uint 64t, UI 64, oops, 64, very large number, 8 bytes. Come on, there we go. So now, this would work, and C and C++ are guaranteed to order things in the structure the way you define them. But what it doesn't guarantee is that things aren't padded. So because we have a 64-bit thing here, what's going to happen is the structure is going to look for the largest type inside of it, and it's going to align everything to that largest type. So it means there might be some padding between these. So what do we have here? We have 4 plus 1 plus 2. That's 7 bytes right here of stuff. So it might actually add another byte of padding right here. Maybe padding, right? And you can avoid that in some cases. Like it may even have padding between these two, or these. Like we don't really know. But you can avoid that if you try to, what do I say? You can avoid it if you make it so that the members of your structure go from largest to smallest. Then the least amount of padding will be required. And that can actually help if you're using like hundreds of thousands of records and structures. You end up saving a lot of space. But what's even better is to make it so that things you use commonly together are right next to each other in the structure, because they're on the same cache line, or more likely to be on the same cache line, so it ends up being faster access. So you can kind of optimize for space if you're in a memory constrained program, or you can optimize for speed when accessing the structure by trying to put things you use together commonly in the same region of the structure, so they're close in memory. So let's do something here. I think there should be a macro in C++ called offset of. If there isn't, I can make it. But let's try that. Say some structure s. I had to say structs. I didn't type def it. I'm gonna say let's see. I don't want to print that. I want to do standard cout. I'll do it C++ way. Offset of. I think it's use something. Let's do offset of. Let's try. I think it's some structure, comma. I think it's use something. Yeah. Let's just see if this actually works real quick before I do anything else. Okay. Let's try and actually run that. So G++, test cpp, out test. Looks like it's happy. Run it. Offset is 0. Cool. That's what I expected, because it is the first thing in the structure. Now I should expect this to be, if this is 4 bytes, it should be at offset 4. 0, 1, 2, 3, 4 would be the 5th byte, right? So I'll put right here 0 through 3. This is going to be 4 through 5. This is going to be what? I guess 6 through 7. Is that right? Yeah, and this will be 7 through 15. Okay, if there was no padding. So let's copy this, and we'll do 1, 2, 3, 4 of them. What did I call them all? We have UI8 small number. Okay, we have slightly bigger number, UI16, slightly bigger number, and then UI64, very large number. Okay. Very large number. Let's just see what this gives us. Okay, do that too. Okay. Where am I at here? Okay. So they're all giving me offset 0, which is wrong. So let me do this. see what's going on here. Okay. Getting there. Oh, right, I never actually picked which thing I wanted to get the offset of. So let's do that. Come on. One more to go. Okay, and we'll try that. There we go. So 0, 4, 6, 8. Let's compare that to what we have over here. So we have 0 to 3, 4. We expected this to be 6, and we expected this to be at, oh, 8, right? Because it ends on 7. Next we have to start on 8. Okay. So it didn't actually end up padding anything weirdly. That's interesting. If I stick something else in here, I'll do like a float F. Let's see what it does now. Okay, so we have 0, 8, 10, 16. Does that seem right? So 0. I would expect this to be... What would that be? Maybe 4 through... Maybe 4 more of those, so 7. 4, 5, 6, 7. That's 4 bytes. Yeah. Okay. And then yes, this would be at 8. And then I suppose this would be at 9 through 10, is that right? So we got 8 here. So it is adding some padding between these two now. So that's interesting. So let's actually show the... I want to make this actually easier to do. I think I should do this in a macro. So I'm going to say something like define show offset. So struct, I'll say S for struct, M for member. Yeah, next line. Okay. I'll allow the person to have the semicolon themselves. So offset of whatever. I'm going to say M. Okay. This is just going to be S. This is going to be an M. I think that should work. So I can just do this. Show offset. I'm going to say some structure. And what did I call it? It was like UI32 some number or something. Is that right? Something. I'll just rename it. Some number. I like that better. Okay. So 1, 2, 3, 4, 5. 8 small number. 16 slightly bigger number. 64 very large number, I think it was. And over here we had a float. Or is it over here? It was over here. Just F. Is that right? I'll give that a try. There we go. 0, 4, 8, 10, 16. Alright, so now what I want to do is actually enhance this a little bit. What do I say? Range. I want to say range of this. It's going to be from 2 things. So it'll be from that up to offset of S member M plus size of the member M. Yeah. I have to wrap that in parentheses. Okay. Now see, I should be happy. Okay, 29. UI32 some numbers not declared in the scope. Well, yeah, it shouldn't be. Can I do S dot M? primary expression. Struct whatever. Let's say 0. So pretend we have a structure at address 0, and take the size of the member at that address. So I should really get the type from that. There we go. That's basically how offset works too. Okay, so 0 to 4, 4 to 8, 8 to 9. Let's make this a little bit easier to read. Say, comma, like that. And at the end, I want to add closing bracket, and we'll end the line. Yeah, I think that's good. Okay. So it ranges from 0 to 4 for UI32 some number. And it ranges 4 to 8, looks like, for F, which is actually, I mean, it's kind of wrong. It should be 4, 5, 6, 7 is 4 bytes. So it's that minus 1. Okay, so it's this whole thing minus 1. Try that again. There we go. 0 to 3, 4 to 7, 8 to 8. So we're getting 1 byte here. And this is 10 to 11. So this right here got padded to 2 bytes. And this padding is going to be different between different compilers, maybe even different versions of the compiler. And it's something you kind of have to be wary of. So, unit 16 taking 2 bytes, that's expected. This is taking 8 bytes, should at least. Should be 16 plus 8 is 24, but we're counting the 16, so it's 23. Okay. Now what we can do is we can actually force the compiler to pack it without padding. And on Windows, there's something like, for MSVC I should say, there's pragma pack. And you could say like how many bytes you want to align to. The minimum is 1. So I could pack to 1 byte alignment, meaning there's no padding. And you could do push, comma 1, which means if I do pragma pop, I think it is, pragma pack pop or something like that, it's going to restore the padding it does to its default. You can also just pack nothing, pragma pack like this, and it does a default. But I could do pop as well. So let's try that and see what happens. MingGW kind of emulates MSVC that way. So let's see here. Yeah, right here, 9, 10. See that? So we have 0 to 3, 4 to 7, 8 to 8, and then 9 right on the next byte. So there's no extra padding added there. And we can see it's 11 to 18. Before this was a lot higher. Things were getting padded. So let's get rid of that again. So right here you can see 10 to 11, and then I would expect it to be on 12 through, 20. Or I guess 12 to 19. Yeah. Anyway, this whole thing here is getting padded to like the nearest 8-byte boundary. And what do we have here? We have 8 between these two, and then we have 3 between these two. So it should make an extra 5 to get there. So 11 plus 5 is 16. So you can see that's what's happening right here. It's adding some padding below these. And we're able to get rid of that. So that's a pretty good way to ensure that when you're writing stuff to files and reading them back out in files, that it'll be read and written the same way between compiler versions and even different compilers, just because you know that the structure's packed how you need it to be. Now for GCC, typically you would use something called like, what is it, __ attribute, __, like, is like double parentheses packed like this. And you can either define that over here before the semicolon, or you can define that over here. And it's the preferred way is to do it over here. They both will work though. Last I checked with the documentation for GCC and G++. Let's see if that works. Yeah, it does. Okay. There was for a while a bug with MingGW on Windows where that wasn't working, and you had to do it like the MSVC way with pragma pack. But it looks like you can do it this way now with MingGW. I do prefer it the Microsoft Visual Studio way, just because you can do a pragma pack, and you can push, and then you can pop it back off. So if there's some kind of weird alignment you're typically doing, and you need to restore that as your default method of packing, you can make it so that it goes back to its default instead of it clobbering the packing scheme for all feature structures. And you also don't have to label every single structure if you want to have some scheme. This way you have to kind of label each structure, which is also fine. I mean, I don't really mind it. And you could also just do this to pragma pack 1 And then you can just over here say pragma pack nothing. It'll go back to default. So that's also legitimate. And that would be kind of your equivalent to Microsoft Visual Studio. Let's give that a try real quick. Just see if it works. Alright, so you can see how it still works. So I'm going to leave this the NingGW way. Return to default packing. Return to previously used packing. Line to 1 and don't preserve old packing scheme. And line to 1 byte boundary, whatever. I don't want to say that. Line to 1 byte, I'll just say. And preserve old packing scheme so that we can return to it. Okay, and this is like the NingGW64/GCC/G++ way of doing it. I'll even say idiomatic. I shouldn't even say that for NingGW, but for these two it is. Okay, so we kind of covered that. Now, there's something else about this that I kind of want to cover. There's something kind of like a structure, but it's more like an alias. A bunch of things you can call the same thing. That's called a union. So you can do union. Let's call it something like, geez, I don't know. Things. And in this union of things, you could have something like a character. Call it C. You could have a, I don't know, uint8t, ui8, call it byte or something. Now, what happens is, if you use this, it's going to fill this whole thing with whatever you use. So the size of this is equal to the size of the largest type you put in here. But all these types are sharing the same space. So if I put like a uint64t, ui64 number, and I actually assign this, these are getting clobbered. And if I assign this, it's clobbering the first byte of this. If I assign this, same thing, first byte of this. I got a float in here, float f thing, whatever. It's going to be 4 bytes, and it's going to clobber everything else in the structure. Or not structure, what union, I mean. So basically, it's like, I might be using any of these things, but I'm not sure which one I'm going to be using at any given time. So rather than having all of these members of a structure, I could pack everything into a union and just use whichever one I need. And it's going to give me enough space to fit all of these things. So that can be kind of useful when you want to save memory, but it's also kind of dangerous to use these because if you don't account for which one you should be using correctly in all parts of your code, you might be trying to use this to read from, but like writing to this or something. Or like maybe writing to this and reading from this, and just getting garbage at the end. So you have to be careful when you use these. But these are great for memory-constrained environments. And you can have things like structures inside of unions, or unions inside of structures, and you can nest them recursively. Like you can have as many structures inside of structures as you want, or as many unions inside of unions as you want. It doesn't really matter. And that'll be coming up in a video I do soon. So it's something to keep in mind. This, I suppose, could have implications on padding as well. So like I said earlier, it wants to pad to the largest type in here, and you saw that it was trying to pad to 8 bytes. And these together didn't equal 8, but these two did, so there was no padding required. And before, when I had just these two, we had, what was it, 5 bytes of padding? And then it'd be 6, 7. So there should have been 1 byte of padding before this. Let's try and see if I can show that off again. Oh, you know what? I have it still packed, don't I? Let's get rid of that. There we go. So let's see, 0, 3, 4 to 4. Aha, so there's 1 byte of padding between these two. There should be a 5 right here. But since this is 4 bytes, 5 bytes, okay, and then adding this to it would give us 7 instead of 8. It put an extra byte between these two. So then this ends up being 0 through 7, and the next one starts on 8. So it is doing what I thought. It's just where that padding happens is kind of unspecified. It's implementation defined. So that padding could have happened between these two, but it happened between these two for whatever reason. Okay, anyway, anything else I want to cover here? So I wanted to cover unions, I wanted to cover like padding and structures, how to order them to make sure that they're more efficient for like reads and more efficient for like memory consumption. I wanted to talk about unions and kind of how they're accessed. Just for fun, I'll stick the union in there, I guess. You can define the union actually inside here too, and like give it a name or whatever. I'll stick it right here. Just see what happens. So 0 to 3, 4 to 7, 8 to 8. There's 2 bytes here between these two. Yeah. I think I need to give it a name. Let's call it U things. Oh, here we go. Look at that. That's interesting. 0 to 3, 4 to 7, start an 8, and then it should be 9 to whatever. But we have that union thing in there. And the union size should be the size of the biggest thing inside of the union. And the biggest thing inside of the union should be 8 bytes. So that's interesting. For aligning to 8 bytes, it seems like we would just say, well, I guess we're already at 8. Like right here we're at 8 bytes. But then we're starting at like 1 byte after that, and the next 7 bytes are wasted, so we'd be at 8 to 15. And then 16 through something should be the next 8. I wonder why it's going all the way up to the next 8 to 24. I would expect it to start on 16. Oh, because I'm not showing it. Right. Okay, so it is probably starting at 16 going to 23. And then this starts in 24. That's what's happening. I'm going to show that actually. So U things right here. Where did I stick that? It was between small number and the next one. Okay, so right here. Show offset some structure. U things. Yeah. So I'm expecting it to be 16 to 23. It is 16 to 23. That's what happened. So I couldn't even use bytes offsets 9 through 15 because there's just a 1 here. But if I reorganize this, it would be more tightly packed. I wouldn't have to worry about that. Like if I stuck this smaller number at the end, you wouldn't have that issue. So let's try that real quick. I'm going to comment this out, and then I'm going to make a new copy of it that's unpadded, unpacked, whatever. So it is padded, it's unpacked. Right. So let's do that. Let's take the largest ones and stick them first. So that's the largest right there. And this is also the largest, it's the same size, because its largest type is UINT64T, 8 bytes. And then it can also use less if it wants. So let's space this out a little bit. Okay, and then we have 32-bit, that's 4 bytes, this is also 4 bytes. This is 2 bytes, and then we have a 1 byte thing. And I'm going to get rid of these because I've reordered it and they no longer actually match what's happening. Okay. Let's see what it does now. So 0 to 7, we have an 8 to 15. Do we have a 16 through something? We do right here. Do we have a 20 through something? We do. Do we have a 24 through something? Yes. And do we have a 26 through something? We do. So you can see it's tightly packed now. So I was able to get rid of all of the packing issues just by sorting it from largest type to smallest type. So I'm glad that went off pretty well. Now there's one other thing I want to show in this, and that is going to be something called Bitfields. And these are something you should never use, but I just want to show that they exist. So let's do that. Put our union thing over here. I want to do, yep, that in the floating point's fine. I want to put this above here. That should be the actual order they're defined. I'll comment this old way out. Okay. There, yeah, now it shows it in order. Cool. So the next thing I want to show is called Bitfields. And what you can do is if you have some number of bits you want to pack, you can actually pack those into single members of a structure. Oops, I'm going to do that. That's a mistake there. So let's make a new structure. I'm going to call this one, how about date time or something. All right. Now in this structure, see we have our year. And our year is going to be some kind of a 4-digit number. Right now we're in the 2000s. Say I only care about it going between like, I don't know, 2024 right now up until like the year 4096. So if 2 to the 10th power equals 1024, then the 11th would be 2048, and then the 12th would be like 4096, right? That means 12 bits is going to get me from 0 to that, right? 12 bits gives me 0 to that number. That's plenty. So I can basically define any type that has at least 12 bits in it. So I could say uint 16t, ui16, I'll say year. I could say colon, the number of bits it needs to take, so 12. Then what I could do is I could say we have a month. Well, months can only ever be between, let's say, 0 and 11, right? Or you could say 1 to 12, but 0 to 11 makes more sense if you're indexing the month. So for that, how many bits do we need? Well, in general, you could say we need log 2 of that number. So log 2 of like 11, right? How would I express that? And the way I think of that is just like nearest power of 2 that is greater than or equal to it. And I showed that, you can include, it's called bit. And you could use, standard bit seal to find it or whatever. That's perfectly fine. You could also do log of the number divided by a log of 2. That'll give you it. And you have to take the ceiling of that, because you can't like have half a bit or something. But in general, I know that, let's see, 2 to the 4th power should be 16, right? You have like 2, you have 4, 8, 16. So that should be plenty, 4 bits. That'll fit in 1 byte. So uint 8t, ui8 month, colon 4 bits it takes. Okay, I'm going to say uint 8t, ui8 day of month, let's say. That's going to be up to 31 would be the largest number of days, so 0 to 30 would fit. So if I do 2 to the 5th power, I get 32. So that minus 1 is addressable, 0 to 31, which should be 1 more than I need even. So 5 bits for the day of the month. Now I want something like hour, minute, and second, so uint 8t, let's say, ui8 hour. How many bits do I need for that? Well, I need to at least be 0 to 59 can be referenced, so if I can get 60, value 60 for the max number when I get the power of 2, that should be plenty. Well, 2 to the 6 is 64, and I could use 0 to 63, so I'm going to say 6, right? Maybe I should even label these, so 0 through 15, oh sorry, 0 through, what am I doing? 4095, and I have 0 through, I should put these in brackets, make it explicit. This would be 15, I have 0 through 31, I have 0 through 63, okay, and uint 8t, ui8 minute, same thing here, 6, 0 through 63 is like addressable, and then, actually I only need 24 hours in a day. I can do less than that, I'll fix that. Second, colon, 6, same thing, 0 through 63. Okay, this one only needs to be, for 24, I can fit it in 5, so 0 31. If I did 4, I'd only get up to 16, which would be 0 to 15 as a range. That's not enough. So yeah, it has to be this. So this is about as tightly as I could pack it. I could do, one smaller, make this 11, and say this is up to 2048, but 2047, because it's minus 1. So that's pretty good. I kind of want to show why you shouldn't use this. It's really hard to word this. But essentially, if you write it with one compiler, or you write it with an executable, maybe with one compiler, and then try to read it with an executable, maybe with a different compiler, it may not be, what do I say, it's the same offsets for each of the bits. Whether it's like little endian or big endian is unspecified. Whether the bits go from least significant to most significant or vice versa is unspecified. It's like when it's packing the bits, it might start like over here and go down, right? And start packing them this way, whatever. But it also might start packing from the other direction, like this. And then, go from variable that way. So, I guess I'll just be simple with this and say, essentially you don't know where the offsets of each of these bits are going to be. And it's going to be different for each compiler, maybe even different version of compiler, since it's implementation defined. So it's not something you can trust when you're sending stuff over like a socket on the internet to communicate with a remote client. And it's not something you want to do for like long-term file storage or something. This is just something that would be okay to use maybe while something's in memory. But even then, it'd be more efficient to pack it yourself. And I'll show how to do that in a second. But first, let's actually use this. I'm going to say something like struct date time. Let's call it dt. I'm going to say dt dot UI30 year 16, I think it was, year equals 2024. I'll say dt dot UI8 month equals, I'll say 8 right now. dt dot UI8 day equals, right now it's 19th for me. UI8 hour equals, right now it is 12 plus, would be 5. Okay, why do I keep hitting equals? I want to be plus. dt plus UI8 minute. Right now it is the 47th minute. Okay. I'm going to do dt UI8 second. I'm going to say it equals 0 because I don't know what the second is right now. I actually want to make something to set these and print them out. I'm going to say set date time. So do that. I'll pass it a struct date time reference dt. Okay. Cool. And I could say show date time const struct reference dt. Okay. I'm going to say cout. Man, I kind of want to, I'm going to do this. Make this easier. Stream iterator of type character. Call it cout. Initialize it with cout. Okay. And I could just say standard vformat 2. I'm going to say year, month, and day. This one's padded 2. This one's padded 2. Okay. These are all padded 2. Oops. Okay. And then standard make format args. I'm really not used to how far away the arrow keys are on this keyboard. It's a huge jump compared to the keyboard I used to use. It was louder. Okay, am I missing anything here? So I need to include some stuff. I need to include iterator for outstream iterator, and then I need to include in cloud apparently. Stream, I need to include format, and I need to build it with C++20 at least to use that. Okay, and let's actually use these. I'll set it, and then it would show it. Is that the other one? Show date time, yeah. So set it. It's going to be dt. Okay. Nope. Oh, come on. Good enough. Now I can do show date time. DTO apparently. Okay. The standard equals C++20. Let's try it now. Okay. Struct date time has no member UI8 day. Okay. What do I call it? Day of month. Right. Okay. Of month. Over here, day of month. Okay, line 80, variable or field, show date time declared void. Yes. Why is that an issue? I'm not returning anything, am I? Oh, right, I didn't actually. Fair enough. I need to actually put the things in there that I want to set, so. Unit 16t, UI16 year, unit 8t, UI8 month, unit 8t. I'm just gonna copy that. I'm really getting sick of that happening. Let's try that again. So month, day of month, hour, minute, second. Second. Come on. Okay, it's going to be UI16 year, UI8 month, UI8 day of month, UI8 hour, UI8 minute, and UI8 second. Okay. Declared void. Why is that an issue? It's not declared in the scope. Show date time, set date time. It was absolutely declared in the scope. What is he talking about? Void set date time. I have the members here. Body starts here. It ends here. I have show date time. Does it not like construct? Oh, jeez. Date time. I didn't never actually name the structure. Yeah. And here's struct date time, whatever. Okay. That was not a good error message, to be fair. Okay, so no matching function call for v format 2, whatever. Right, I didn't say where to format it to, so format 2. I need to give it a outstream iterator. Okay. Test. Okay, so here's our date. 2024, 08, 19, and 17, 47, whatever. So that looks good. And it should be packed into some bits. Let's look at the size of that structure now. So, standard cout, size of date time, in bytes I'll put, okay, and then, oh, come on. Yeah, and then do this. Wait, that's not where I want that. In bytes. Oh, that's why, because it justified everything. Or unjustified, or whatever that stupid thing is. Okay. God, that's confusing when that happens. I'm gonna say, size of... I use struct. Struct date time. I should have typed F it to make it easy. Okay. So it's 8 bytes. That's pretty small. So if I look at the actual structure here, what do we have? We have 2, 3, 4, 5, 6, 7 bytes. So it's actually bigger than you'd think it would be. And if you look at the number of bits, we have 15, 20, 25, then we have, what, 31, and then we have 37. So it should be 37 bits total. But we actually have 8 bytes, was it? Yeah, 8 bytes. 8 bytes equals 64 bits. Which is fine, it's probably doing some kind of padding or something. So let's do, I'll do it the idiomatic way. Attribute, say packed, see if that helps anything. Seven bytes. That's a little bit better. So 7 bytes be 7 times 8 is 56. Is that right? Yeah, that's right. Okay. That's still a bit more than our 37 though, and we can do better. And like I said, if you write this out and read it back, it's implementation defined, so you might not get what you expect on different executables made with different compilers. So I don't like this method. Easy though it may be, and even though it is saving some space compared to 1, 2, 3, 4, 5, 6, 7. Yeah. So let's show how to do that. What I'm going to do here is I'm going to say I have a new datetime object here. And since I know I can fit it into, say, 7 bytes, I'll do UI8t. In fact, how many bits was that I wanted? It was 37 bits. I'll double check just in case I made an error here, because this needs to be right. So 11 plus 4 plus 5 plus 5 plus 6 plus 6. 37. Yeah, 37. So 37 bits should fit into 5 bytes. And the way we're going to fit this into the 5 bytes is by ORing the bits we need in from the source values like the year, the month, the day, the month, the hour, the minute, and the second. And we need to do that by shifting these values over with masked bit ranges into that array at the appropriate locations. And we'll do the reverse when we want to take the bits back out. In order to show this, I'm actually going to cut ahead to future me with this already coded out a little bit, because it's going to be a bit complex to reason through. And I'm going to want to make some changes to the date-time structure so that the bits are packed as neatly as they can be, and so that I can utilize all of the bits. Because right now, if I'm using 40 bits, there's going to be 3 bits wasted, because I'm only using 37 right now. So I can add those to the year and have a higher range. So I'll show that in a second. So here I'm going to show how to pack a date time into an array of bytes in a way that will be cross-platform. So what I'm going to have here is a bunch of things being ORed into an array of uint8t's. I'm assuming I have 40 bits packed into here, which is 5 bytes. So LPUI8 array, date time, position 0 is the first byte, 1 second byte, third byte, dot dot, whatever, right? We're going to be using that a lot. I'll leave that there for a second. But for the year, when I OR something in, I can't OR a value greater than 255 into a single byte. Otherwise, it's just going to get truncated. That's why I'm casting this to a uint16t, so I can look at the first 2 bytes of this. So position 0 and position 1. So I'm going to say the value at this position, UI16 date time, is going to equal, I'm going to say UI16 year. So I could just stick that in there verbatim, but I'll be a little bit more crafty, and I'll say I want the first 11 bits of it. Or I think I decided on the first 14 bits for the year. So I'll say 14 bits. So if I shift 1 to the left 14 times, it's going to give me the first 14 bits, or the 14th bit being set. If you imagine 0 being the first bit, if I have 1, shift to left 0 times, I still just have 0, or I'm going to still have 1. So that's the first bit still. Right? If I shift to left 14 times, it's going to be, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, whatever. I'm going to have whatever this is. Right? So you can imagine 4, 8, 12, then it's going to be 13, 14. So the 15th bit is set here. So now if I subtract 1 from that, you can imagine, since these are all zeros, I'm just going to have a 0 here in place of it, and then all of these become 1s. Right? So I have 14 bits set. 4, 8, 12, and then it's 13, 14. So that works. Anyway, so I'm doing that. If the year is greater than that, it's going to be truncated to that many bits. Now what I want to do is actually want to insert more stuff into here. I'm going to say UI8 array, date, time, position 1, because we've already used the whole first byte, and we've used 6 bits of the second byte, right? Imagine we have 14 bits. 8 plus 6, right? So we have 2 bits left in this. So now I'm going to say OR into this, since we already have the first 6 set. We don't want to mess with those. We're not going to say equals. We're going to OR in 2 more bits if they're set from our source. So our next source is going to be the month. So UI8 month ANDed with, I only want the first 2 bits here. So do the same trick. 1 shifted left by 2 minus 1 to get those first 2 bits being set. So just to show that off, it'll be, right, if I have 1 here, if you're shifting to the left twice, it's going to be 1, 2, right? And I subtract 1, it's going to give me that 2-bit set. Okay, so I'm adding it with that. But now, what I need to do is I need to shift this over in a place that's not going to overlap the existing 6 bits. So I'm shifting to the left over, I'm shifting it to the left 6 times. So those 2 bits that I just grabbed from the month are at the end of this second byte of LPUI8 array date time. Okay, so now we're on the second byte, or sorry, third byte of the LPUI8 array date time, which is offset 2, 0 being the first. Okay, it's going to OR equal, or it could just equal at this point, because it's a new byte. We need to use the rest of the bits of the month. Well, the month has 4 bits in it, so I have 2 more bits to mask out. So I can do almost the same thing here. I'm going to say UI8, UI8 month, and I'm going to say 1 shifted left twice, -1, so the first 2 bits. But then I'm going to be a little more crafty and shift that to the left twice. So now imagine I had something like 0, 0, 0, 0, 0, 0, 1, 1. Okay. Now I'm shifting left twice right here. So I'm grabbing those next 2 bits of the month that I passed. Okay. And that is what I'm going to OR in. Except I don't need to OR it because it's a new byte. And I also don't want it to be over here. I'm grabbing these 2 bits, but I want these 2 bits to be over here in the byte when I put them in. So this whole thing needs to be shifted to the right twice. Kind of reversing this. I'm pulling it from here, but I'm sticking it here. In here, the 3rd byte of the packed array. Okay. Now we have 2 bits taken of byte 3. Okay. So now what are we doing? Now we're going to say, we're still on byte 3. It's going to OR equal. Now we have UI8 day of month, which has how many bits? It has 5 bits. That'll still fit then, so it'll be 2 taken, plus 5 more taken to be 7 taken, so 7 bits taken. That was byte 3. Okay. So day of month, I want to grab the first, what is it going to be? 5 bits I said. So 1, shift left 5 times, -1. Okay. So we're doing that. We're pulling that from the day of the month. But then this whole thing we need to shift left a bunch, so it doesn't overwrite the 2 bits you've already taken. So shift left twice, so it happens after the 2 bits of this byte that are set by the remaining bits of the month that didn't get covered in the 2nd byte. Okay, so I have 7 bits taken. So now we're still on byte 2. We're going to OR equal. It's going to be UI8 hour. But we're only taking the first bit this time. Okay. And we want to shift this to the left, to the last possible position. So left 7 times. So you can imagine I have 0, 0, 0, 0, 0, 0, 0, 1. If I shift that left 7 times, we'll get 1, 2, 3, and 4, 5, 6, 7, right? So we'll have that, the last bit being set. Okay. But now I need to use the remaining bits of the hour, and we're on the 4th byte now. So that's going to just equal, this is the first time we're using it, UI8 hour, and we're going to AND out the remaining, how many bits are used in an hour. So there's 5 bits for the hour. We've used 1, so we need the remaining 4 bits. So 1 should left 4, -1. Okay. Alright. And then we need to do that shift left once. Because we're masking 4 bits, and then we're shifting those 4 bits we're masking over. So 1, 2, 3, 4, 1, 2, 3, 4 are set right now. Shift left once. We've already used the first bit of the hour in the previous byte of the date time pack array, right? So we're going to shift this left once, so we're going to get 0, 0, 0, 1, 1, 1, 1, 0. So we're masking this from the hour to get the last 4 bits of the 5. But then we're going to say 0, 0, 0, 1, 1, 1, 0, shift left. After that, rather, I'm going to shift it to the right 1 time. And that's because when I actually store it in this new byte, I want it to be starting at the first bit of that byte. Come on. It's going to equal 0, 0, 0, 1, 1, 1, 1. Wait, 0, 0, 0, 0, 1, 1, 1, 1. Like that. There we go. So now it's actually starting at the first bit of this when it gets stored. Okay. What do we have left? We have the minute, so LP, UI8, array, date, time. Still on here. We've used how many? 4 bits used? 4 bits used. Byte 4. It's going to equal, I'm going to say UI8 minute, and it's going to be 1 shifted to the left 6 times, I want to say. -1. Okay. And that's going to need to be pushed over by how many bits already used. We've used 4 already, so 4. And will that fit? I don't think it will, because we have 4 bits used, and we have 6 bits to put, that'd be 10 bits. So we can only actually grab 4 from this to have 8 bits total. So grab the first 4, and move it over 4 places. So we have 2 bits left in the minute. So 4 out of 6 minute bits used, 8 out of 8 bits of byte 4 used. So now LPUI8 array date time position, or offset 4 I should say. It's going to equal, this is an OR right here, so I don't clobber the existing bits. The remaining 2 bits. So now 6 out of 6 minute bits used, 2 out of 8 bits of byte 5 used. Okay, we're getting there. This is going to be UI8 minute, and I'm going to do 1 shift left twice. I want 2 bits. That minus 1. Okay. And then this whole thing I need to shift. What else? I need to shift this over by 4 bits that I've taken already. Okay. And then that gets shifted to the right 4 bits. So you can imagine I have something like 0, or sorry, I'd say there's like the 6 bits, right? I've already masked these first 4 out, and I have these 2 left. So I really only want to mask 2 of these. Oh shoot. Over here I mean. And I'm masking 2 of these. So in order to get that, I'm saying I have that I'm creating with this right here, and I shift it to left 4 times, so I get 1, 2, 3, 4. Right? So I'm masking those 2 out, and then when I'm done, I shift it to the right 4 times. Gives me that. Okay. So it's stored in the right place. So now I have LPUI8 array, date time, still position 4 on the 5th byte, or equals this time. It's going to be the second. So UI8 second, and how many bits I use? 2 out of 8? Yeah, we're only using 2 here. So now I have 6 more to use. That'll be all 8 out of 8. So really all I have to do here is the second masked by 1 shift to the left 6 times, how many bits I want, so minus 1. Okay, and this whole thing I'm going to shift to the left how many bits I've already used, which is 2. 2. So now 6 out of 6 second bits used, and 8 out of 8 bits of byte 5 used. Okay, so that should actually packed now. That was a bit difficult to do all that. Now I need to make the opposite of this function, which is an unpack. So I'm just going to paste that actually. Oh, I already had a version of that I could have used. I'm going to get rid of these then. Okay. Cool. So if I pull from this, I can say dt dot UI16 year equals. Now let's pull this out. It's going to be LPUI16 date time masked with 1 shift left 14, the number of bits I want, minus 1. There. So that was easy. Get that one basically for free. Okay, dt UI16 month equals, it's going to be from here. I'm going to and out the bits that I set. So I want to and out. I might just want to do this from scratch, really. It's going to be the last 6 bits. How many were used for this? So for this we used 14 bits used equals 8 plus 6. So I need the last 2 bits of this. The remaining 2 bits for part of the month. Okay. That's going to be just 1 shift to the left 2 times, minus 1, to get both those set. And that whole thing I'm going to shift to the left 6 times to get the last 2 bits. Okay. And after I do that, I need to shift that to the right twice. Or, sorry, 6 times, to get that in the beginning of this variable. Yeah, okay. And then we're going to do dt UI16 month or equals, so we're adding to that, opui8 array, date, time, on the third byte, and we're taking the next 4 bits of it, so 1, shift to the left, 4 times minus 1, okay. Once I get that, I actually need to shift it left by the number of bits I've already set in the variable, which is going to be, what, 2? I took 2 bits from this. Yeah. So this gives me the remaining 4 bits. Okay, so how far in are we now? We've used 2 bits of byte 3 used. Okay, let's do dt.ui8. Wait, this should be 8. 8. It's going to be day of month equals, and it's going to be opui8 array, date, time. We're still on byte 2, and we've used 2 bits of it. So how many do I need for the month? It's going to be 4 bytes, I think, or 4 bits, I mean. Because 2 to the 4 should be 16. That should be right. So I need 4 bits. I'm going to say 1 shift left 4 times minus 1. The first 4 are set. Then I need to shift that left by how many spaces over in the current byte of the packed byte array it is. So I've used 2 already, so shift left twice. Okay. And whatever that gives me, I need to shift that to the left, or to the right, I mean, twice. Okay. And now how many bits are used? Should be 2 plus 4, should be 6 bits of byte 3 used. Okay. I'm just going to get rid of these. I'm going to say dt.ui8 hour equals, and it's going to be opui8 array, date, time, position 2, which is the 3rd byte, and I have 2 bits left in that, which is going to be 2 to mask, so that minus 1. To hit the last 2, I need to shift to the left 6 times. Okay. And then take all of that. We're going to shift that back to the beginning, so to the right 6 times. Okay. That's only 2 of the hour, though. So 8 out of 8 of byte 3 used. And how many of the hour? We have like 5, I think? Because it'd be 32. 0 to 31. Could be referenced, and it's only 0 to 23 for the hours. So yeah, it's 5 bits. And we've used 2 out of 5 bits of hour used. So dt ui8 hour, I'm going to say or equals this time to add to it. opui8 array, date, time. Now we're on the 4th byte. So it's offset 3. Okay. It's going to be... How many bits are left? 3. So 1 shift left 3 times, minus 1. Okay. And then once I actually grab that, I need to shift that to the left to where I'm storing it in the variable. I've already used 2, so shift left twice. Okay, now I have dt ui8 minute equals, it's going to be ui8 array, date, time. It's going to be from the same byte offset, byte 4. So how many bytes have I used, or bits have I used from the 4th byte? I've used 3. 3 used from byte 4. Okay. So now, how many do I need for the minute? I'm going to need 6, right? Well, 3 and 6 is 9, that's too many. I can only pull 5 out, so 1 shift left 5 times, minus 1. Okay. I have to shift that to the left. How many bits I've already used? 3 times. I've already used 3. Okay. Neat. And then I have to shift that to the right 3 times now. So I have used 8 out of 8 bits used from byte 4. And then I've used 5 out of 6 bits from minute used. dt ui8 second, sorry, no, minute, going to be or equals, I'm going to say opui8 array, date, time. Now we're finally on the 5th byte, position 4 here. we're going to say, how many bits do you want? Just the last one, right? So use 3 here for the hour. So use 2, then 3, should be 5. If I use 3, which means there would be 5 out of 6 left for this one. Okay. I used 5. I need the last bit now. So it's going to be that on 0x01. So use the first bit of the new byte, and then we're going to shift that to the left, however many bits we've already used, which is 5. So it'll be in the 6th bit place. Okay. IDT UI8. Second, it's going to equal LP UI8 array date time, and it's going to be 1 shift to the left. How many bits I want? I want 6 bits. That minus 1. Okay, I have to shift that to the left. How many bits already used? And I used 1 bit of the byte already. That's what I'm masking with. And I'm going to shift that to right once, so it's in the right place. And I feel like this is wrong because I should end exactly on the last 6 bits of the byte, which means I should have started on 2 bits inside of this byte being used. So 14, 4, and then I have 1 here. Why am I only pulling 4 out for day of the month? I'm actually pulling out 5 bits. That should be 5, but how many do I have left? I have 6 bits used to by 3. I'm actually pulling out 5 for the day of the month. What the heck? Okay, so that means 7 bits of this are used. That's where the problem is. Okay, and then I have... How many bits am I masking here? Just 1? Well, if I'm just masking 1 bit, I could just... It's really just 1 shift to the left 7 times. That made that math a lot easier. And I move that back 7 times after I pull it out of the byte. Like that. Okay, but this is messed up now. Because I need to pull out remaining 4 bits of this. And I'm only shifting over 1 time this time, so I'm only grabbing 1 bit before. So this means that I actually have 4 bits being used from byte 4. And that means I can only pull out 4 bits here. It comes from 1 further. I had to push it back 1 further. Okay, so it's 8 out of 8 bits used for that, and I have 4 out of 6 bits used from the minute now. In this case, only 1 out of 5 used. And it's 5 out of 5 bits of hour used. Okay, and we're using, for the minute, we're only using 4 out of the 6. Okay, and over here we're getting the other one. There are 2, rather. So I need 2 out of this, which is going to be 1 shift to the left twice, minus 1. We're getting 2 bits out of that. It's a new byte, we can do that. And then we're shifting that to the left, how many bits you already used, which is 4. Okay. Now what do we have here? So we've used 2 bits used of byte 5. 6 out of 6 bits used from minute. Which means I have 6 bits left. Okay, so this is going to be 6 out of 6 bits used from second. And we have 8 out of 8 bits used from byte 5. That works. Okay. Are these good too? I guess I'll give it a test. We'll see what happens. So I've already down here made it so I have a little test here to run on. Okay. Unpack date time. Let's do dt packed from UI array date time. I think that was the order I did the arguments. I guess we'll find out. Yeah, 2024, 08, 19, it's 18, 38, 27. So what I put is 18, 38, 13. So 18, 38, 27 is wrong. When I grab that out, I'm only shifting that to the right once, even though it's coming from the last 6 bits, which means I already used 2. So that might fix it right there. There it is. 2024, 08, 19, 18, 38, 13. So that's how you can bit back things. Just for fun, I'm going to show how to do this in a way that is always little endian, perhaps. I think that might be a good thing to do. I need to swap the first 2 bytes of this. And when I do that, the order of the bits are still going to be like how you'd expect with little endian, even if it's big endian. But I could say something like, if I have uint 16t, ui 16 value equals 0x, I don't know, 0001, then I can check if uint 8t, okay, reference to ui 16 value equals 1. And I'm going to say standard cout little endian. If this were big endian, you would actually go from highest value in memory to lowest, like this. When you actually iterate it through it in RAM, it would be stored backwards. So this should actually show me as little endian real quick. I just want to try that real quick. Oh, come on. Expected primary expression before that. Did you? Yeah. Fine. Little endian. So that works. So if little endian, we're not going to do anything special. We're just going to do this. Else, we can do this. I'm going to paste that in here. I'm going to say... Wait, what am I doing? That's not the right one. That's always going to be the same. Okay. What I want is this right here. Otherwise, what we'd say is... There's a standard swap we can do. I'm going to say... It's easier. I'm going to say... uint 8t, ui8 year part 1. uint 8t pointer to ui8 year part 1. Oops, sorry. 16 year. Reference that. Okay, and then part 2 is going to be that plus 1. Okay. Then what I can do is I can standard swap those. UI8 year part 1, UI8, oops, 8 year part 2. So I want to show standard cout. I'll just say UI 16 year, just to see if that works. Swapped year. Okay. It needs to be in this case. Okay. There we go. And is that right? What if I go to calc? Let's say go to programmer. I'm going to say 2024. So in hex, that's 7E8. So what I expect is 087E if I reverse it. So let's do 59399. So E807. Yeah. 07 E8. So that is proper. It worked. It swapped it. So that should work. And usually with big endian systems, the bits aren't actually swapped. Like if you have something like 0x0101, or that's bad, 0100, it'd be reversed in actual memory, right? For big endian versus little endian. So 0x0001. But the actual bits inside, if you have something like 00000001, this is still like the least significant bit, even in big endian. It's not going to swap to be like this or something. There are situations where there's like bit endianness and it matters, but that's never the case I've seen. So this should handle that case for big endian. If someone thinks I might be mistaken about that, please let me know in the comments, but I think this should work. Anyway, I've covered unions, I've covered structure padding, we've covered how to avoid the padding, how to preserve like how much padding you previously had if you want to change it with packing, with push and pop, and how to restore the default but just like pack by itself, nothing in there. We talked about the difference between MSVC versus like GCC, G++ for this attribute packed thing. Sealing probably has its own thing, but I haven't really used sealing much, so I don't know. Anyway, I hope someone found this helpful. And if you have any comment suggestions or questions, please post those. And if you liked it, give it a thumbs up. Consider subscribing for more content like this. And I will catch you guys later. Have a great day.